Have you ever noticed how a bulb glows brighter as the voltage increases, but not in a straight or predictable way? That's a classic case where Ohm's law doesn't apply. Ohm's law says that voltage is directly proportional to current, double the voltage, and the current doubles too, right? But in real life, things aren't always that neat. Many materials, and almost all electronic devices, show behavior that deviates from this simple rule. As shown in the diagram, instead of a straight line, the actual voltage-current curve bends away from linearity. Such materials are called non-ohmic. They break the rule, and they do it for good reasons. Let's explore the first type of deviation, when voltage is not proportional to current. Take a filament bulb as an example. As it heats up, its resistance increases. That means even if you keep increasing the voltage steadily, the current won't rise at the same rate. This causes the voltage-current graph to bend, forming a curve instead of a line. As you can see in the VI diagram from your textbook, the straight dashed line represents ideal ohmic behavior, but the real curve deviates as current increases. So, temperature changes or internal heating can make a material non-ohmic. Now let's flip the voltage and see what happens. In ohmic materials, reversing voltage direction reverses current symmetrically. But in some devices, like diodes, the response changes entirely. Apply voltage in one direction, current flows. Reverse it, and almost no current flows at all. In the VI graph of a diode, notice how current grows steeply in one direction and flattens out in the reverse. So here, the direction of voltage matters, violating the symmetry assumed in Ohm's law. Now imagine something even more bizarre, where the same current can exist at more than one voltage. This happens in certain advanced semiconductors like gallium arsenide. Look at the VI curve of GaAs, it loops. You can draw a horizontal line and find it intersects the curve at multiple points. This means that for one current value, there are multiple voltage states. That's not just a deviation, it's a breakdown of the basic Ohm's law assumption of a single-valued relationship between V and I. So, if these materials don't follow Ohm's law, are they still useful? Absolutely. In fact, they are essential for modern electronics. Devices like diodes, transistors, LED, and thermistors rely on nonlinear behavior to do things ohmic materials never could, like switching, amplification, and temperature sensing. Understanding these limitations helps engineers design circuits that are smarter, more efficient, and more adaptable. Think of it this way: while Ohm's law helps us understand the basics, breaking the law opens up possibilities in advanced technology. Let's quickly recap where Ohm's law does not apply. First, when the VI relationship becomes nonlinear, like in filament bulbs. Second, when the direction of voltage affects current differently, as seen in diodes. Third, when the VI graph isn't a single curve, as in gallium arsenide. Ohm's law is a powerful tool, but it has limits, especially when we deal with materials that are temperature sensitive, direction sensitive, or quantum in nature. I hope you now have a deeper understanding of how voltage and current don't always dance in a straight line. See you in the next session, where we'll explore how different materials, conductors, semiconductors, and insulators are classified based on their resistivity.